You know, usually when we talk about a major technological marvel, there's this expectation of layering.
Right, yeah, the more the better.
Exactly. It's like the modern philosophy of engineering, right? You take a great thing, and to make it better, you just you add more to it. More sensors, more code, more processing power.
Yep, absolutely.
It's like building a high-tech suit of armor. You just keep bolting on new weapons and gadgets and microchips until the thing is basically invincible.
I mean, that is definitely the philosophy that dominates the automotive industry right now.
Yeah.
We've been totally conditioned to equate extreme digital complexity with absolute capability.
Right.
Like, when in doubt, just let an algorithm handle it.
But then you step into the world of top-tier customer racing, and suddenly that entire philosophy gets turned completely upside down.
Oh, completely.
Which brings us to today. Welcome to today's deep dive, everyone. We are looking at an engineering paradox today that is honestly just mind-blowing.
It really is wild.
We're synthesizing a massive stack of sources for you today. Honda's internal engineering white papers, homologation spec sheets, and some incredibly detailed track test telemetry data.
Heavy reading, but totally worth it.
Definitely. And our mission today, to figure out how Honda took a car defined by its digital brain, threw all of that cutting-edge technology right in the trash, and somehow created an analog racing legend. I am talking, of course, about the Honda NSX Gr.
Oh, man. It is the absolute definition of addition by subtraction. And what's so fascinating here is just how extreme that subtraction actually had to be.
Okay, let's unpack this for everyone listening, because the contradiction here is wild. The base car for this, right, the second generation 2016 NSX, the NC1, it was literally named for a new sports experience.
Right, the whole marketing campaign was about the tech.
Exactly. The street version was famous for this insane system called Sport Hybrid SHAWP. It had 3 electric motors. You had a twin motor unit in the front, a direct drive motor in the back.
Yeah, it was this total symphony of electronic torque vectoring.
But this GR4 racing version, they just ripped all of it out.
Every last bit of it.
If I'm wrapping my head around this correctly, it's like taking off an Iron Man suit, expecting to find just a regular guy underneath, but then realizing the guy underneath is like an Olympic decathlete.
Uh-huh. That's a phenomenal analogy.
Yeah.
Taking off that digital armor, all that all-wheel drive line tracing, the active posture control, the hybrid torque management, it exposed the incredibly pure analog potential of the base chassis.
Wow, but why? Why would you take out the very thing that makes the car special?
Well, to understand why they did it, you really have to look at the GR4 rulebook.
Okay, the regulations.
Right. This category dictates production-based racing cars. Complex hybrid systems and excessive electronic driver assists are strictly forbidden. You simply cannot race them.
But wait, customer racing implies it needs to be drivable by everyone, right?
Right.
From a seasoned professional to maybe a gentleman driver who just bought the car to have fun on the weekends?
Yeah, mostly.
So removing the all-wheel drive and the computer assists, wouldn't that make the car significantly harder to drive, not easier?
You would think so, yeah. But in the world of endurance racing, the complex systems that work beautifully on the street actually become severe liabilities.
Really? How so?
You need a car that is robust, mechanically predictable at the absolute limit of physics, and honestly, easy for a pit crew to maintain. Simple, mechanical grip beats complex code every single time when you are pushing a car for hours on end at maximum stress.
Okay, that makes sense. Less stuff to break.
Exactly. By removing the hybrid system entirely, Honda returned the car to the purest, most classic sports car layout mid-engine, rear-wheel drive.
Classic MR setup.
Yep. They took a highly computerized, heavy street car and turned it into a 400 and 360 kilogram analog weapon.
All right, so let's get into the guts of this decathlete. Because you don't just pull the computers out and call it a day, right? The remaining mechanicals have to be absolutely flawless.
Oh, they do. And they are.
So let's talk about the heart of this machine, the engine. The sources emphasize the JNC1 engine. It's a 3,493cc V6 twin turbo.
A masterpiece of an engine, truly.
And I noticed immediately in the research that the cylinder block and heads are sandcast by Cosworth, which, for anyone who follows motorsport, is an absolute legend.
Oh, absolutely. Cosworth's involvement means this block was designed to withstand extreme thermal loads and, cylinder pressures that would just melt a standard street block.
Right.
But the true engineering marvel of this engine isn't just who cast it, it's the geometry. Specifically, the 75-degree bank angle.
Okay, hold on. You're losing me and probably a few listeners there. What exactly is a bank angle, and why does 75 degrees matter?
Sorry. Okay, so think of the V-shape of a V6 engine.
Yeah, the two banks of cylinders.
Exactly. The angle between those two banks is the bank angle. Most are 60 or 90 degrees.
Right, I read that 60 degrees is used because it naturally balances out engine vibrations for a smooth ride, and 90 degrees is used so manufacturers can cheaply share production lines with their V8 engines.
Spot on. So choosing a 75-degree bank angle sounds like a massive, expensive engineering headache just to make the engine a tiny bit flatter.
Yeah, why go through all that trouble?
Because in racing, gravity is your biggest enemy. And a flat engine allows you to manipulate gravity.
Color me intrigued.
That 75-degree geometry allowed the engineers to mount the engine incredibly low in the chassis. In fact, the top of the engine block sits lower than the top of the rear tires.
Wait, really? That is practically scraping the asphalt.
It's insane, yeah.
I assume dropping all that dense metal down so low drastically drops the car's center of gravity.
Drastically. It reduces weight transfer during hard cornering, which keeps the car incredibly flat. But to mount the engine that low, they had to implement another crucial piece of racing tech, the dry sump lubrication system.
Okay, yeah, what on earth is a dry sump? Most racing fans know it prevents oil starvation in high G corners by using external scavenge pumps instead of a traditional wet oil pump. But looking at these schematics, it seems like Honda didn't just use the dry sump for lubrication. They used it purely as a spatial hack.
They absolutely did. So a standard street engine has a deep oil pan at the bottom, right? The oil pools there, and a pump sucks it up.
Right.
Under massive lateral G-forces, the oil sloshes away from the pickup tube, the engine pulls in air, and bam, you get catastrophic engine failure.
Yikes. Not what you want in an endurance race.
Definitely not. A dry sump removes that deep pan entirely. It stores the oil in a tall external reservoir instead.
Oh, I see.
But as you pointed out, the brilliant side effect here is clearance. Without a massive oil band hanging off the bottom of the engine, Honda could drop that 75-degree V6 even lower into the subframe.
Shaving crucial centimeters off the center of gravity, that is just a masterclass in packaging.
It really is.
But taking this back to the removal of the hybrid system, I actually have a big question about the power delivery.
Give me.
On the street car, Honda used those front electric motors for what they called torque fill. When you stepped on the gas, the electric motors gave you instant power to cover the gap, while the exhaust gases took a second or two to spool up the turbochargers.
Right, to eliminate turbo load.
Exactly. So if you rip those electric motors out, doesn't a heavily turbocharged V6 become incredibly peaky? I'd imagine you'd just be sitting there waiting for power, and then suddenly it all hits you at once.
That is the exact problem the GR4 engineers had to solve. And they did it purely through mechanical ingenuity and thermodynamics. Without the electric crutch, they had to rely on incredibly precise wastegate mapping and mechanical anti-lag tuning.
So they basically had to tune the engine to keep the turbo spinning, even when the driver's foot isn't fully on the throttle.
Yes, exactly.
Yeah.
By precisely manipulating the timing and the fuel mixture, they can keep high-energy exhaust gases flowing through the turbine housing at all times. The result is this remarkably flat, almost naturally aspirated feeling torque curve. The engine generates 44.2 kilogram force meters of maximum torque at just 3,800 RPM.
That's really low in the rev range.
Yeah. And it holds a peak power of 400 horsepower right up at 6,700 RPM.
So the driver just gets exactly what they asked for, the exact millisecond they step on the pedal. And speaking of immediate physical response, we have to talk about the gearbox. The street car had a very smooth, very advanced 9-speed dual-clutch transmission.
Beautiful transmission for the street.
Right. But the GR4 version threw that out for a 6-speed sequential gearbox. Now, a dual clutch is already lightning fast. Why go backward to a sequential and drop 3 gears in the process?
Well, a dual clutch is fast, yes, but it achieves that speed by basically having 2 heavy gearboxes bolted together, pre-selecting the next gear.
Oh, so it's heavy.
Very heavy, complex, and highly prone to overheating under endurance racing conditions. A racing 6-speed sequential is designed for one thing and one thing only: violent, direct, mechanical engagement.
Violent is definitely the word.
There were no synchronizers to smooth things out. You pull the carbon fiber paddle, and a mechanical dog ring literally slams the next gear into place with zero hesitation.
And I imagine dropping those extra gears And the whole dual clutch mechanism saves a massive amount of weight hanging out over the rear axle, right?
Exactly. It centralizes the mass of the car, reduces thermal load, and provides a mechanical directness that a street transmission just cannot match. Every shift sends a physical shockwave right through the chassis.
Man, well, that provides the perfect transition because you now have this dense, low-slung power plant throwing violent instant torque to the rear wheels and a dogbox transmission sending shockwaves through the car.
It's a lot of stress.
Right. The standard aluminum chassis of the street car would probably twist itself into a pretzel under that kind of pure mechanical stress. How on earth are the bones of this car holding it all together?
The chassis really is where the GR4 transitions from a great race car to an absolute masterclass in material science.
Okay, tell me more.
It utilizes a multi-material space frame, incorporating extruded aluminum and carbon fiber floor panels. But the defining breakthrough, and this is the first in the entire automotive industry, is a patented manufacturing process called ablation casting.
Okay, I was reading the white papers on ablation casting and it completely blew my mind.
It's so cool.
But for anyone who isn't, a metallurgy nerd, break down why traditional sand casting wasn't enough for a car hitting violent track curves at 150 miles per hour.
Right, so in traditional aluminum casting, you pour molten metal into a sand mold and you wait for it to cool slowly. The problem is that slow cooling makes the crystalline structure of the metal quite coarse, and a coarse grain structure leaves the metal brittle.
Ah.
It might be strong under a static load, but if you hit it with a sudden kinetic shock-like launching over a track curve, it can just snap.
Which is exactly what you do not want in an endurance race. So how does ablation casting fix that? Is it basically like taking a glowing hot blacksmith sword and plunging it into a barrel of water to freeze its strength?
That is the exact physical principle, yes.
Oh, awesome.
With ablation casting, they pour the molten aluminum into the sand mold, but they don't let it cool slowly. Instead, they blast the mold with high-pressure water jets.
Whoa.
The water literally blasts the sand away. It ablates it, while simultaneously flash cooling the molten metal inside.
So it freezes the molecular structure of the metal instantly.
Precisely. That rapid, violent cooling creates an incredibly dense grain structure. The resulting aluminum suspension nodes have the ductility of a forged piece of metal, meaning the ability to absorb massive energy without snapping. But you get the complex, hollow geometry that is only possible with a cast piece.
That is brilliant. It means the suspension geometry won't shift a single millimeter, no matter how hard the driver abuses it over a curve.
Exactly.
And speaking of structural hacks, taking out the massive hybrid battery pack from behind the seats didn't just save weight, it left a giant gaping hole in the middle of the car.
A huge void.
Yeah. I initially thought they just, threw a piece of carbon fiber over it to make it look pretty, but the specs say they welded a massive rear bulkhead there instead.
Nature abhors a vacuum, and race engineers abhor wasted structural opportunities. Instead of just leaving that space empty, they welded and riveted a massive solid aluminum bulkhead right into that cabin, permanently dividing the cabin from the engine bay.
It's like a flimsy wooden bookshelf, right?
Huh.
If you try to push a cheap bookshelf from the side, it sways and folds, but the moment you nail a thin piece of plywood to the back of it, it becomes totally rigid.
Yes. It acts as a giant shear panel. That rear bulkhead tied the main cabin to the rear subframe so tightly that it drastically increased the dynamic torsional rigidity of the entire vehicle.
Wow.
It essentially locked the front and rear halves of the car together into one immovable block.
It is so clever, just using the absence of the battery to make the car structurally superior. Though I did laugh when I read they actually had to install a rear-facing camera system because that new wall completely destroyed the driver's rear visibility.
Yeah, a very small price to pay for a stiffer chassis. But once you have a chassis that stiff, you have a new problem.
What's that?
You need to stick it to the road. You need downforce.
Okay, yes, let's talk aero. I was looking at the homologation specs, and it surprised me that they didn't just slap a massive hill climb style rear wing on it.
Right, they kept it relatively clean.
They rely heavily on the flat floor and the rear diffuser to generate ground effect. But doesn't relying on a vacuum underneath the car make it incredibly sensitive to ride height? Like, if you hit a bump and the car lifts, doesn't that break the aerodynamic seal, causing you to lose all your downforce instantly?
You've just hit on exactly why those ablation cast suspension nodes are so critical.
Ooh.
The suspension is so rigid and precise that it keeps the car's ride height perfectly static, even under extreme aerodynamic load. And because the car sits just 1,106 millimeters tall, and is incredibly wide, they made the entire underside perfectly flat.
So how does a flat bottom actually suck the car down?
It's basic fluid dynamics, specifically the Venturi effect and Bernoulli's principle.
Okay, walk me through it.
As the car aggressively slices through the air, that air rushes under the flat bottom. As it moves toward the back, it hits the massive rear diffuser, which expands to space.
Right.
This accelerates the air traveling under the car. Because the air under the car is moving significantly faster than the air over the top of the car, it creates a powerful low-pressure zone.
It literally creates a vacuum that sucks the car down onto the pavement.
Exactly. And the absolute beauty of ground effect is that it generates massive, reliable downforce without adding significant topside aerodynamic drag.
Which a big wing would do.
Right. If you rely purely on a giant rear wing, that wing creates drag, which acts like a parachute slowing down your top speed on the straights. Ground effect gives you the phenomenal grip in the corners without sacrificing your straight line velocity.
Okay, we've got the physics down. We have this ultra-stiff, ground-sucking, mechanically pure chassis. But I wanted to translate these white papers into what the driver is actually feeling through the seat of their fire suit.
Oh man.
Because honestly, it sounds terrifying and amazing.
It is an absolute beast to tame. You have to remember the new weight distribution.
Right.
Stripping out those heavy front electric motors left the car with a 42 to 58 front to rear weight distribution.
So only 42% of the car's weight is over the front wheels.
Exactly. On the street car, if you turn the wheel into a corner, those front electric motors would actively pull the nose in. They force the car to turn.
But with no front motors and almost no weight over the front tires, this thing must understeer like a dump truck if you just casually turn the steering wheel.
It will simply plow straight forward. The front tires do not have enough vertical load to generate mechanical grip.
So what do you do?
To get this car to turn, the driver absolutely must master the art of trail braking. You have to manually manipulate the physics of the car.
Okay, you've hit us with trail braking. If I'm sitting behind the wheel, what do I actually have to do? Are you basically weaponizing the brakes to artificially shift the car's weight?
That's a great way to put it. You fly toward the corner, dive deep, and smash the brake pedal to squash the front tires into the pavement.
So the nose dives under heavy braking, maximizing the front tire's contact patch with the asphalt.
Yes, but the trick is the trail part. As you begin to turn the steering wheel toward the apex, you cannot just let off the brake instantly, or the nose will pop back up and you lose your grip.
I see.
You have to slowly release or trail off the brake pedal in perfect synchronization with your steering input. If you time it perfectly, utilizing that ultra-stiff chassis, the turn-in is razor sharp. You feel the tire grip the asphalt straight through the steering column into your hands.
Wow. So the driver has to physically manage the weight transfer in real time to force the front end to bite. That sounds incredibly demanding.
It is, but it's deeply rewarding.
But what happens once you are actually in the middle of the corner?
Well, mid-corner is where the MR layout really shines. Because the heavy engine is sitting right behind your shoulders, the car has a very low polar moment of inertia.
Right, it's like an ice skater pulling their arms into their chest to spin faster. All the mass is centralized, so it naturally wants to rotate.
Exactly. The chassis is so stiff, there is zero lag between you turning the wheel and the car reacting. Every tiny slip, every micro texture of the asphalt is telegraphed straight through the carbon fiber bucket seat, right into the driver's spine.
That sounds incredible.
It is, but that ease of rotation is a double-edged sword. Here is where the danger zone begins.
I was waiting for the catch. If it rotates easily into the corner, it's going to rotate even faster if things go wrong on the exit.
The exit is terrifying if you do not respect the machine.
Yeah.
When you hit the apex and decide it's time to accelerate out of the corner, you step on the gas. Remember, there is no hybrid torque management here.
None at all.
That turbocharger spools up, and all 44.2 kilogram force meters of torque slam into the rear wheels exclusively.
And 58% of the car's weight is sitting directly on those rear tires.
Which gives you incredible mechanical traction initially. But if you're too greedy with the throttle and you overcome the friction limit of those rear tires, that low polar moment of inertia, the ice skater spinning, suddenly works against you. The car will initiate a violent snap oversteer. Because all the mass is in the middle, it acts like a pendulum. It will spin faster than a front-engine car ever could.
And unlike the street car, there is no computer to save you. No all-wheel drive system is going to detect the slip and magically pull the nose straight.
Nope.
There is no traction control algorithm dialing back the throttle for you.
None. You are entirely on your own. It demands lightning-fast countersteering and millimeter-perfect throttle control to catch the slide before it puts you into a wall. It is an incredibly demanding, physical car to drive. It does not tolerate a lazy driver.
Just you, millimeter-perfect throttle control and lightning-fast countersteering. It sounds like an intoxicating analog dance on the absolute edge of physics.
It really is.
It doesn't tolerate mistakes, but when you get it right, the physical and emotional feedback must be totally unmatched.
It is a pure reflection of the driver's skill. The car isn't managing the physics for you. It's simply giving you the most capable, rigid, highly engineered tools possible to manage the physics yourself.
And that, I think, brings us back to the ultimate truth of this machine. We started by asking why Honda would take a technological marvel and strip it bare.
Right.
And the answer is that the NSX Gr. proves that true, enduring speed doesn't come from a million lines of computer code. It comes from perfect, purposeful, physical design. The armor was just a bonus. The strength was always in the bones.
It really is. But looking at how drastically capable this car became once the digital safety nets were removed, it leaves you with a deeply provocative question about where automotive engineering is heading today.
Oh, what do you mean by that?
Well, think about it. In an era where every modern street supercar and hypercar relies on infinite lines of code, active aero, and digital torque vectoring just to keep you on the road, are those cars actually engineering marvels?
Oh, wow.
Or have we just built incredibly fast digital cages that are keeping us from experiencing true, pure driving? If taking away the computers makes a chassis this much more communicative and capable, you have to wonder if the absolute peak of the driving experience is actually already behind us, locked away in the analog era. Think about that the next time you turn on your traction control.
Wow. Are we driving the cars or are the cars driving us? That is an incredible thought to end on. Thank you to everyone for joining us on this deep dive into the Honda NSX Gr. Next time you see a high-tech machine covered in sensors and screens, take a moment to wonder what it would look like stripped bare, and appreciate the analog brilliance that might be hiding just beneath our digital world. Keep questioning, keep exploring. We'll see you on the next deep dive.